about the estimation of parameters in linear regression models. It's so estimation of the parameters that we have is like that. How can we calculate beta 0, beta 1, beta 2? And this is going to be, this is just a review again. But we have, like, when I say it's review in chapter 2, like less than 50% is review, comparing like to the basic statistic that we have. I'm adding more things to that we would use it quickly in next chapters. Okay. In the basic statistics, we had that when we wanted to calculate the parameters, we would go with the different estimation methods. And for our estimation, for example, one was the maximum likelihood estimation of the linear regression parameters. To know what's the method of maximum likelihood, you can go to second year stat notes that we have on Learn, and then go to chapter 6. Like in the next second half of the chapter 6, you will see the likelihood function. So it's basically, we are going to write down the equations and then get the derivatives. But so go and check that one, please, if you have question, or if you don't remember it right now, what was the likelihood function. So now assume that we have our, we would say for epsilon, this is the way that we write down for the normal distribution. We say our distribution, we consider it has the normal distribution, and then the expected value, the mean for the epsilon is 0, and the variance is the matrix I times like sigma 2. And as I said, this sigma 2 has the variance and covariance. Because of that, we need to consider like multiply that by I. And then we would say y, matrix Y is equal to like x times beta, the true value for beta, and then plus epsilon. So we can say for y, the distribution for y is going to be like normal distribution, and then x times beta, this is our expected value, our mean, and our variance is going to be I sigma 2. The multivariate normal probability density function that we would have, and we had this one before, we had the equation of the normal distribution. I also think that even we talked about that before. It's like that we have it like n, we would write in z of the, like, for example, n, and then mu, normal distribution mu, and variance. Just this variance, it's variance covariance. It's not just like you, because we have multivariable. When we had one variable, we were working with one variable, simple linear regression, we didn't have the problem. Or the situation that maybe our independent variable, like x1, x2 independent variables that we have, they would have some covariance, like they collinearity together. So because of that, we would need to consider the variance covariance when we are working with the multivariate. And then the function, this is the normal distribution function. We had this one before in the chapter 1, and as well as like in the basic statistics. Even if you look at the like z table, on the top of the z table, this function is written. However, over there it's just for one variable, here is for multivariable. And then for the dependent variable y, we can write it down as fy, because z is when we had like the standard form of it. Okay, here is a review as well. So what we do is that we want to minimize our likelihood function of beta. Please go and check to see that what is the likelihood function. It's very simple. We just multiply like different probabilities of the functions that you have. It's going to take, it would be like probably one whole lecture if you want to talk about it. But if you go and check it by yourself, it's going to save lots of time for us. And you're going to use this equation at the end. So this is the equation that we use for the estimation of the parameter. So maximizing the likelihood function of beta is equivalent to finding the value of beta, which minimizes z of beta. Just a quick flashback is like when you have a likelihood function, it's like you would try to have a normal distribution curve, and you want to, because mean, our expectation is always in the center, so we try to find out what's going to be in the middle, like on the center, which is the maximum. So that's because of that here you will see that this is the maximizing likelihood function of beta. But the equation that you're going to use in this course is this one. So I wouldn't ask you for proving any of the equations as I told you before. We are working on the applied statistics. So it's a beta estimate. Our estimate is going to be x prime x and then -1, x prime y. So make sure that you know how to do these calculations. However, you can use your calculator as well, but you want to make sure that you would know this, how to do this, because if I give you conceptual questions, you might need to use it. Like, I wouldn't ask you to do the whole calculation because it's going to take time, and in 1 hour quiz that we have, you wouldn't have time for it. But the problem with the calculators is that they're going to give you the final answer, but I might ask you to give me something in the middle, like some elements in the matrix that you would have in the middle of the process. So make sure that you know that how to do these calculations. It's the mathematics. Like some students, they had it in their like high school. They have learned about matrices. Even if not, in the first year, like undergrad course, engineering computation, we learn all about, like even, I'm not talking about the calculus course and those ones, just the course. I taught this course before. I know that we covered this over there, and like with the matrices. So we also call this one ordinary least square estimator as well. But just know that what's the beta that you would use, like beta estimate is this. This value of beta is always the least square estimator of beta. It's the maximum likelihood estimates, as I said, if they are normally distributed. This is an example. So you have the example in front of you. This is our model, the model that I want you to fit it in it. And I'm going to give you the, like, you have the data as well. The example is a review example. So the reason that I wrote it down here is that you would just do that by yourself and check your final answers with this one. See that if your the beta that you will find out is going to be like this. And basically, it's just this equation that we would use. It's like that. You would find out x prime x, and then you would get the -1 of it. It's symmetric. And then you would multiply. You would need to find out this one as x prime y as well. So x prime y, and then when you multiply these two, you're going to get the beta estimate. Yeah, so here it's like that. Before going to the inference, by this one, like as the beta x prime x -1 times x prime y, the reason that I say that it's better that if you could do that by hand, I mean, you would need to do that by hand to know how to do that, is like, because when we want to find out the variance, and the variance equation, it has the x prime x -1 inside it. In fact, it's like x prime x -1 times sigma 2. So if you do this one here for like counting like beta estimate, when we want to go with the variance covariance, it's going to be easier for you to calculate that. Make sure that you're going to look at the practice problem and tutorials that we have. It has examples on this. So when we find out the beta estimate at the end, the first one is going to be our, like, you have it beta 1, beta 2, beta 3, right? So beta 1, beta 2, beta 3. So these are going to be your betas. You're going to put it, like, instead of beta 1, you are going to put 4.083 plus like 0.109 x1 plus, like, you would write it down like this. You would just substitute the values in it.